Okay, so what we are going to talk about now is a prelude to the finite elements method. I'm going to talk about standard discrete systems, and you will see why I want to talk about this. Now, when you take a system as a whole, sometimes it is very difficult to understand what's going on. You would rather like to understand, it is simpler to understand the parts of a thing. So let's, for example, we have all read that poem about the 6 blind men who went to see the elephants. And one of them catches hold of the tail, one of them catches hold of the trunk, and they get completely different pictures. And when they put all this information together, possibly they can get the picture of the elephant as a whole. In physics too, we sometimes need to do that, in the sense that when we try to understand the entire problem in its entirety, it may be very difficult to grasp the behavior. And therefore, what we would like to do is we would like to break it up into small parts, and we would like to understand how the tail behaves, how the trunk behaves, how the ear behaves. And then we would like to meaningfully put this information back together to get a picture of the whole elephant. This process of subdividing the system into their individual components is essential to breaking up the system into elements. So what we will do is we will take the whole system, divide it up into its small elements, study each element separately, and then we have to rebuild. We have to have a way, a means of rebuilding the original system from an understanding of the behavior of the components. In reality, we actually do that all the time. Now here, before I go further, I would like to distinguish between discrete systems and continuous systems. Continuous systems, when we talk about continuum, when we talk about continuous systems, what are we essentially talking about? We are actually talking about a continuity which extends from minus infinity to plus infinity. And therefore, if I want to deal with continuous systems, I need to invoke the mathematics of the infinitesimal. So I have to consider infinitesimal quantities. I have to set up equations in terms of infinitesimal quantities. And as a result, my solution would involve differential equations, and it would also involve an infinite number of elements. This may be cumbersome. This may also be not needed very often. I mean, sometimes we as engineers are used to making approximations, but not only engineers, sometimes even for a real understanding of the physical system, it is not really needed that we need to understand. We need to go to the, we need to understand, or we need to analyze the continuous system. What can we do? We can work with discrete systems. What is discrete systems? Discrete systems means we try to break up the continuum into a finite number of its components. Now, it doesn't mean we can just take an infinite number of things and just arbitrarily say, oh, I'll work with 10 or I'll work with 5. It's not like that. There is a kind of science behind it. There is a kind of understanding behind it. And we need to be able to understand to what extent and in what manner we can break up a continuous system into a discrete system. The main difference is that in a discrete system, we use a finite number of elements. Of course, the easiest example that you have of discretization is, let's say, in curve fitting. For example, let us imagine that this red curve that you see here is your real curve. It is possible to approximate this red curve with a straight line. You could have simply taken a straight line. Let me again annotate. You could have simply taken this red line and approximated with a straight line, the red curve with a straight line, the green one. Would you like that? You would not. You would not like that because you can very well see visually that this leads to large errors. The green line is nowhere near what the red curve looks like. Can I remedy that? Yes, I can remedy that. What I can do is I can use the yellow curve that you already see here, where I am using straight lines, but I am using a larger number of straight lines. I'm not using a single straight line, but I am using a larger number of straight lines. And in this case, you can see that your approximation is not too bad. It's an approximation you probably can live with, depending upon what it entails. I mean, what is the physical meaning? Why are we talking about discretization? Because discrete problems can be solved with computers, even if the number of components is large. So even if it means that I have to break up this red line, not into 1, 2, 3, 4, 5, 6 segments, but a very large number of segments, I don't mind. Once I have computers, I can work with that. I'm not afraid of a large numbers, but I am afraid of continuous spaces. I need my system to be discretized. So discrete problems can be solved with computers even if the number of components is large, whereas continuous problems can only be solved exactly by mathematical manipulation. Now here you have to understand the difference between an exact solution and an approximate solution. The green line that I had drawn is an approximate solution to the red curve, approximation of the red curve. So suppose the red curve is a solution to some problem. If instead of that red curve, I give you the green curve that I had drawn, I give you an approximate solution, whereas the red curve, I would imagine, let's say it has been obtained mathematically by an exact solution. So it is the exact solution at every point. So even in between these points, whichever point you choose, any arbitrary point matches the exact solution exactly. There is no error. But even if you break it up in a very large number of discrete elements, looking at this, the yellow, the combination of this yellow line segments looks good enough. And you see here at these points, which I have marked with these notes, they do match. But look here, the red line is here, the yellow line is here. The red line is here and yellow line is here. So everywhere there is a mismatch. So with a discrete solution, you will not get an exact solution. You will get only at best, you will get an approximate solution. At best, the approximate solution can be so chosen that the error is small or the error is more often acceptable. But there will always be an error. Whereas if you solve a continuous problem using mathematical manipulation, what you will get is an exact solution. So remember, all discretizations involve an approximation, and our aim is to make sure that this approximation approaches the true continuum solution. Now, if I want to make the approximate solution approach the true continuum solution, what do I need to do? Who will tell me?
Reduce the error. Reduce the error and reduce the error.
Reduce the error, yes, but how would I reduce the error?
By choosing large number of points.
One person at a time, you identify yourselves or you switch on the camera and speak. Yes, Hitesh, continue with what you were saying.
Ma'am, we can increase the number of nodes.
Yes, you can increase the number of nodes. What does that mean? You're increasing the number of discrete components.
Yes, ma'am.
So you can go for finer discretization. You can increase the number of discrete variables. As you increase the number of discrete variables, the discrete solution, which is an approximation, would probably approach the true continuum solution. That is one way. There must be other techniques as well. So this is about discretization and continuum. So in a nutshell, what I have been trying to tell you is the continuum is divided into a finite number of parts. These parts are called elements, and the behavior of each element is specified by a finite number of parameters. So therefore, you take each element and you try to understand or you try to describe the behavior of each element by a finite number of parameters. And then after that, solution of the complete system is necessary as an assembly of the elements following the rules applicable to standard discrete systems. I imagine at this point, all this kind of sounds like mumbo jumbo. Let me explain what I mean by this. And then you will see that you have been doing it all your life. You take the continuum, you break it up into parts. These parts I call elements. I take each element at a time and I describe the behavior of each element by a finite number of parameters. What these parameters are, I'll come to later. So once I have done that for each and every element, once I have done that for each and every element in my continuum, I put these elements back together, which is called assembly of its elements. And this assembly of its elements will follow some rules. You can't just do that. I mean, you can't just do that in any which way. It will follow certain rules. And these rules are applicable to standard discrete systems. Once you have assembled them back, you will be able to obtain the solution of the complete system as a whole. So to go back to my analogy, you will have to know how the tail behaves, how the trunk behaves, how the tusk behaves, how the ear behaves. I've forgotten what are the other parts. Then you can't put the tail at the front and the tusk at the back. You will have to know how to put them in their right positions. So the rules which are applicable to standard discrete systems tell you how to assemble the parts. And once you have assembled the parts properly, at that time, you would be able to obtain the solution of the complete system. As I said, you have been doing this all your life. Very often, I forget who told me that they had difficulty trying to understand finite element method from the mechanical engineer's viewpoint. In most books, you will see what they do is, yes, it was Hitesh. You will see that what they do is they invoke the spring mass system. We don't have to do that. We have been doing it all our life in our electrical networks. We've been doing circuit theory. And what have we been doing in circuit theory? Remember, the circuit theory is again a model. This is a model of my system. And this, let's say I've taken a part of the total. Let's say this is my total system, just for illustration purpose. Now, there are several branches in this circuit, and they're all interconnected at certain nodes. What I do is I take out one of them. So this is my IJ branch. I just take it out separately. Now, if I look at this branch, what I need to know is I need to know that this is the equivalent resistance of this branch, RE. And I have, so this is my element. I have two nodes, I and J. At element I, read this J as I. This is again a typo, this J as I. So I have current IJ flowing in at point J, and I have current II flowing in at point I. And I also know that the potential at node I is VI and potential at node J is VJ. So what do I know? I know two values of two parameters at only the nodal positions. So I know that IIE, the current that is flowing in the element from I towards J, is IIE equal to 1 by REVI minus VJ. Similarly, I can write IJ, which is flowing in, sorry, this is II, IJ flowing in at point J towards I, IJE only in element E is equal to 1 by REVJ minus VI, which means I can write this equation in matrix form in terms of I's and V's. So IIE, IJE is equal to 1 by RE, this matrix 1 minus 1 minus 1, 1, VI, VJ. So I have now established a relation between parameters of the single branch. So solution of the complete system, sorry, what did I say? The continuum is divided into a number of parts. So I have taken each individual branch, and the behavior of which is specified by a finite number of parameters. Am I not doing that? I am specifying the behavior of branch RE or E in terms of the currents II, IJ and the voltages VI and VJ. So this is my relation, IE is equal to KEVE. Remember, everywhere I am using the subscript E, which means that I am not commenting about the current at node I or node J anywhere else except the part which is flowing in the ETH element. So IE is only that part of the current at I or J or wherever, which is constrained in the branch E. And that is dependent on VE, the nodal voltage vector VE, which is again the voltages only at VI and VJ. Of course, the voltages cannot change if it, no matter which element it belongs to. And I have a constant K, which is again relevant to this particular element E. Now, I can do this for each and every branch. We do that. But each and every branch is not going to give me a complete solution. To get the complete solution, I need to assemble these branches individually back together into the complete network, mathematically. How would I do that? So I'm going to ask Nishant to answer this question. I have a large number, 1, 2, 3, 4, 5, 6. I have 6 branches or 5 branches. And what I have done is for every branch, I have set up an equation like this. So I have I1 equal to K1 V1, I2 equal to K2 V2, etc. Now when I have done that, my first part is done. The continuum is divided into a number of elements and the behavior of each element is specified by a finite number of parameters. Now I need to assemble these branches together in such a manner that I can obtain the complete solution. How would I do that? Which rule would I use? Don't look at this slide.
Ma'am, we have to place branch one by one.
Yes, we have taken every branch one by one.
Yes.
And I have obtained an equation like this for every branch. Now, what rule can I use to assemble all the branches together?
The KCL rule will be used.
KCL rule, yes, absolutely. Yes. So that's exactly what we do. We use KCL or we use KVL. Since here we are dealing with point quantities, we will work with KCL. To assemble the whole network, we will assume current balance. So we will take the point PI, this is your point PI. At this point, I will assume current balance. And I will find out what is the total current entering here. The total current entering here will have contributions from 1, 2, 3, 4 branches. So all the branches which are adjacent to this node have to be considered. So I will have 4 equations like this for all these branches, 1, 2, 3, 4. I'll take them all together and I will do this. The total current entering I is equal to PI equal to summation over J and then summation over E, Kij, Vj. Look at this carefully. The first summation, this summation is over node J. So I have to do this exercise not only at point PI, I will have to do it at every node, right? KCL has to apply at every node. So therefore, I have written the equation for node PI, but I will have to repeat this for every other node as well. And when I'm calculating the value for PI, I do summation over not all the elements in my circuit. It is sufficient to do the summation over only those elements I to M, which are connected to this particular node. And when I do this, so I get a big matrix relation. This is 2 into 2 matrix relation. I'll get a matrix equation. P is equal to KV, where P consists of all the currents, Ij, etc.
Sorry, I'm having trouble understanding right now. Please call later.
Okay, Himanshu, you will have to crop that out. That is my Alexa trying to attend my class. Yeah. So where was I? P. So when I have P, my P will be a matrix. P will be a vector of all the currents at all the nodes. So all the nodal currents will form a vector. That is your I vector, or P as I call it here. And P will be related to V, the voltage vector, which will also be the nodal voltages. So V1, V2, V3, V4, etc. And the relation between the current vector and the voltage vector will be given by this constant K, Kij being summation E equal to 1 to M Kij over all E. So what I have done here is I have shown you something that you have always done. When you are doing electrical circuits, you take the whole circuit, break it up into elements. Here the elements are the branches. Each branch at a time, you set up a relation in terms of the nodal currents and the nodal voltages corresponding only to that branch. Once you have done that for every branch, you will have to look a rule which allows you to assemble all these currents and voltages together. In case of electrical circuits, you can apply KCL at every node in the circuit. If you apply KCL at every node in the circuit, using these local relations, you will be able to end up with a global relations which involves all the nodal currents, a vector of all the nodal currents, a vector of all the nodal voltages, and P and V will be related by a global constant vector, global constant matrix, which is given by Kij. Is this clear to everybody? You will see later that in finite element analysis, we do something very similar. I'm using this example because this is an example that is very familiar to all electrical engineers, if not all engineers. Once you do this, I'm going to give you the formal definition. I'm going to put up a formal assignment in your hello. This is the relation. This is the assignment that you will have to do. This is your first assignment, which you will have to upload on hello. You will have to look under assignments for that. I'll put it up. So you have this circuit. This is an arbitrary circuit. I want you to write out a relationship for this circuit in the standard discrete form and solve it. So you can choose values of G1, G2, etc., I1, I2, whatever values are necessary. You can solve, you can assume the minimum number of given conditions you can assume, and you can solve it, but it has to be solved using this method. So the steps are important. Of course, if you have a circuit, you can always solve it. But that is not what I want you to do. What I want you to, I mean, you can work with the variables, you don't have to solve. What I want you to do is I want you to set up this equation so that if you can feed it into the computer will be able to solve it. This is your first assignment. I'll stop here. Okay, this is kind of what I'm doing is, here I'm setting out the methodology because I'm going to use this later. Whatever we have discussed, I'm setting out it as a formulaic manner. What exactly does it involve? What exactly does this discretization process involve? Firstly, I mean, it's easy in case of electrical circuits because you've been doing it all your life. Identify a set of discrete parameters Vi, which describe simultaneously the behavior of each element E and of the whole system. This is important. See, I told you, the current in branch I may be quite different from the current in branch J, but voltage at J cannot change from branch to branch. When you are considering this branch, Vj is the same as the Vj that you're considering when you are considering this branch. So there are certain global quantities. So firstly, you have to identify that. Identify a set of discrete parameters Vi, which describe simultaneously the behavior of each element E and of the whole system. Vj does not change when you consider the elemental V or when you consider the global circuit. Now, what is this? Sorry. Next, what you do, for each element, a set of quantities IIE, so these are elemental quantities, can be computed in terms of the system parameters, often with a linear relationship. So IIE is equal to G1 and GI1, EV1, etc., etc. So it is in terms of V1, V2, etc. There can also be an Fi, which is a source quantity. After that, you can obtain the system equations. The system equations will be in the form of GV plus F equal to I. This F will be present if there is a source vector. This F will not be present if there is a source vector. Once you do this, see, for example, in this case, you don't really need to identify. You know that the voltages are the first set of parameters and the currents are the second set of parameters. Once you establish these relationships, you will be able to realize what constitutes F. And you will be able to solve this. And what you should do it, you should write out every step in such a way that in the next assignment, you're able to feed it into a computer and solve it. Yes, so that brings me to the end of standard discrete systems. In the next class, I will begin to talk about the finite elements method. In the meantime, you should practice electrostatic field problems, the basics, and do this exercise. Any questions?